This is part 3 of chapter 8.1. We now, what we talked about previously was sampling distributions. What does that mean? How are the values of a distribution compared to the population? We then moved on to an important term called standard error, which is an adjusted standard deviation divided by square root of n, which applies to sampling distributions. That leads us to something called the central limit theorem. Sounds important, central limit theorem. And so what that says in the central limit theorem is just that the sampling distribution of means, as the sampling distribution of the means becomes approximately normal as the sample size increases. So there's a direct connection, and we had kind of seen that somewhere all right here. Or the standard deviation decreases, but in this case what we're looking at here is the sampling distribution of a mean becomes approximately normal as the sample size n increases. The bigger your samples, the more normal the distribution becomes. And this is regardless of the population distribution. An important note that we end up talking about in future lessons is what if the distribution is not normal or it's unknown, then the distribution of the sample mean is going to be normal, or the sampling distribution will be normal, provided that the sample size is greater than or equal to 30. That's why we like bigger samples, so that we can apply our results. So with the central limit in mind, let's go ahead and apply another problem here. Here's a distribution. Here's a population distribution, mean weight of 30. Or a sampling distribution, and the standard deviation is 12.9. Now, weight gain during pregnancy is skewed right. So an obstetrician obtains a simple random sample of 35 low-income patients, determines that there is a mean weight gain during pregnancy of 36.2 pounds. Does this result suggest anything unusual? And so in this case here, what we're looking at is what's the probability, right, that the mean weight would be greater than or equal to 36.2 pounds. So what we do is do a distribution here. You would draw one. The mean is 12.9, but we want to take into consideration, because the original data is skewed right. The original data is skewed right here. We need to verify, at least in this case, our n equals 35, which is greater than 30. So because of that, we can use the normal model, which means we can use this, and then we use the adjusted standard deviation, the standard error right there. And so you do 12.9 divided by square root of 35, which is 5.32. And so again, right here, we can use the normal model if the sample size is greater than or equal to 30, which it is. And so in this case here, we are looking to see the probability. Here's 36.2. What is the area over here? What's the probability that a mean weight gain of 36.2 pounds? And we get 0.417. Where does that come from? Well, again, go to StatCrunch, normal calculator, 30, and what do we need for standard deviation? 5.92. So we would put 30 in here. This would be 30. This would be 5.92, and we want this to be a 36.2 weight gain greater than, and then there's your 0.147. Get it from there. And so it's a 14% chance that 35 women will have a mean weight gain of 36.2. Is this unusual? What's your answer before? This is not unusual, right? Why is it not unusual? Because it's greater than 5%. Not unusual here, right? We have the 5% rule that you need to be mindful of. So that's it. 8.2 is 8.1 is very similar to 7.2, just using the adjusted standard deviation. That's the end of part 3. We'll do these practice problems in class.